Okay, so now that we've finished the review section, we're going to begin tackling the first fundamental problem of calculus, which is developing a method for computing the slopes of tangent lines. Now, on the surface, this may not sound like a very rich problem, but remember that the slope of a line is defined to be rise over run. And if you want to compute the slope of a line directly using this definition, you're going to need 2 points which are known to be on the line. But if all we have is a curve that a line is tangent to, calculating the slope using this traditional method will not work because you only have 1 point that's on the line, in particular the point at which the line is tangent to the curve. So this is where calculus comes in by developing a tool called the derivative. And among other interesting applications, one natural motivation for being interested in the slope of a tangent line is that it may be used to provide a definition for the instantaneous velocity of a moving object. That is, how fast it's going at a particular instant in time. So in order to discuss this application accurately, we need to start with position functions. So that's what we're going to start with now. So this section is about position and velocity. So we're going to start by talking about what a position function is. So that's the definition we're going to fill in here. A position function is what? Well, this definition kind of tells you what a position function does. So it mathematically models the position of an object moving in one dimension as a function of time. So let's actually zoom in on this one dimension part for the moment. What do we mean by moving in one dimension? Let me give you a couple of examples. Okay, so one example would be walking along a path. Let's talk about why that's one-dimensional. And if it helps, it may help to imagine it as a straight path for now. Okay, so what can you do when you're walking along a path? You can follow it. You can just keep following the path, or you can turn around and go backwards. Right? There's really only those two options. And if it helps, think of it as a narrow path. Because if it was a really wide path, you might start to argue, oh, well, you can move from side to side. And then that really confuses things and makes it not a very good example. So imagine a narrow path, one where you can't really move from side to side. Imagine it's so narrow that if you're walking behind somebody, you aren't able to actually pass them. Just for the sense of having a picture in your head. Another example might be climbing up a rope. Actually, let's be less specific. How about climbing on a rope? Okay, so what are your options if you're climbing on a rope? You can climb upwards, or you can climb downwards, right? Or you can let yourself slide down the rope, or you can climb back up the rope. There's really only two options. So what do both of these examples have in common is that at any point in time, there's two options. You can go forward or backwards, right, if you're in the case of the path. And in the case of the rope, you can go up or you can go down. There's really only two options. So that's the idea here. When you're setting up a position function, what you're going to want to do is you're going to want to identify those two directions. In the case of walking down a path, you have either forward or backwards. And in the case of climbing on a rope, you have moving up the rope or moving down the rope. You want to identify those two directions with halves of the real line. So let's, that was supposed to be a Y. Key idea here. Let's just draw a sketch of the real line. So you have a number 0, which you could think of 0 as like a starting point, either on the rope or on the path or in any one-dimensional space that you happen to be moving around in. So to the right of 0, or to the right of the origin, we have a positive direction, which means you're moving this way. Okay, and you also have a negative direction, which is the other half of the real line. Okay, and the idea is when your motion in one dimension, you identify the two different directions that you have available to you with different halves of the real line, and usually you'll identify a particular point on the path or a particular point on the rope with the number 0 on the real line. Okay, and how you do that exactly is usually left up to you in the specific situation. You have some flexibility. But usually there's a natural choice, as we'll see in the next example. So let's take a look at this example. And we'll go through the words in a moment, but really what you have here is you have a ladder. This line here is think of this as the bottom of a wall, and then you've got like a sidewalk. So imagine there's a hole in the sidewalk. And if you go down that hole, there's a ladder. And you can climb down that ladder and you'll go down through a pipe. And where that pipe leads, you can just use your imagination. Maybe it goes down into the sewers where the Ninja Turtles are, or something like that. It doesn't matter too much. Or you can climb up the ladder and you'll go up the wall, right? So that's the idea. And then there's some place where there's a sidewalk, and then you can already see ahead. I've labeled that as ground level. Okay, so that's the picture in mind. But the idea is every point on that ladder is going to be identified with a point on the real line. And the way we do that, let's take a look. But let's read the example a little bit closely first. So we've got a ladder emerging from an underground pipe and climbs the side of a building. We've kind of already illustrated that by what we just mentioned, pointing at the picture, right? So identifying up as the positive direction and down as the negative direction. So if I pause there for a moment, what we're really talking about is now we've got a positive direction moving up, which we're going to associate with the positive half of the real line, and moving down the ladder, we're going to identify that direction with the left half of the real line. That discussion should be present in any model where you set up a position function. But let's keep going. So we may use a position function to realize locations on the ladder as points on the real line. Okay, and that's kind of just what I just said, so there's nothing new there. Now the position function actually won't be discussed until after this diagram. I just want to go through what's on this diagram at the moment. So remember I said there's some natural point usually on your one dimension of motion where you can identify that point with the number 0 on the real line. And in this case, the natural place to do that would be ground level, right? Imagine if you're walking along the sidewalk and you say, oh, hey, there's a ladder. Right? I can climb up, or I can climb down, or I can do nothing at all. I can just stand here and stare at it. But whatever the point may be, at that height that you're standing on at that point, that's a really good place to identify with the number 0. And then the rest of the identification you can see is given by these two examples. If I count upwards based on the rungs of the ladder, 1, 2, 3, 4, you can see I've labeled this as 4 rungs above ground level. That's identified with the real number 4. And then the other example is if I go down instead and I count downwards, 1, 2, 3 rungs now down below ground level, that would make sense to identify that with -3, which is right. Even you can see if it's 0 and that's -2, this must be -1 and this must be -3. So the idea is each rung corresponds to a unit on the real line. Okay, so, and fill in the rest on your own, right? I'm not going to write every single example. You can do another one for exercise, though, if you want to fill it in. If I went up 2 rungs, this point here, that's 2 rungs up the ladder, that would be identified with the number 2 on the real line. And if I just went down 1 rung from ground level, that would be identified with the point -1. So each position that you could possibly occupy on the ladder is identified with a point on the real line. That's the important part. And you need to have that mapping set up before we can identify or model motion on this ladder with a position function. But now that we've got that set up, we've got this identification nailed down, we can go ahead and talk about a position function. So here's where it's introduced. So let S of t, S is typically the letter we will use for position function. It's not strictly necessary, but it's standard to do so. So that's what we'll do. So we'll let S of t denote the position of a person climbing the ladder at time t. So t is the input value for the function. That's going to represent time. And usually you want to specify your units at this stage too, right? And that's exactly what's happened right after this comma. So where t is the time in seconds, so t is definitely time, but it's in seconds since the point at which they began climbing. So t equals 1 is going to correspond to exactly 1 second after the climber began climbing, and t equals 0 would be corresponding to exactly the moment in time when the climber started climbing. You could even have negative values of t, right? If based on this definition of the units for t, if you had t equal to -1, that would correspond to the point in time 1 second before the climber started climbing. And now whether or not that's going to make sense for your position function is another story, but that's how you would interpret it if you set up your time variable like this. Okay, so just to give you an example about how to use the language here, I've got a table. There's 2 columns. The idea is the first column is going to contain mathematical statements using the position function. And then on the second column, it's going to be descriptions, the corresponding description of what that mathematical statement means, but just using ordinary language. So we can, let's start with the first row. There's 1 missing in each row, so we're going to fill it in. So for the first row, let's the statement, we need to fill it in, but we can jump to the meaning. So the climber is 4 rungs above ground level 6 seconds after they begin climbing. So their position is 4 rungs above ground level. Well, that maps to the number 4 on the real line. And the point in time that we care about is 6 seconds after they begin climbing. So based on this definition of t, that would mean t is equal to 6. So we can write this with a mathematical statement by saying s of 6 is equal to 4, right? 6 seconds after they started climbing, their position on the ladder was 4 rungs above ground level. Okay, so the next one, we're given the statement and we have to supply the meaning. So this says s of 0 equals 0. So the point in time is t equals 0. In other words, the point in time we're talking about is right when the climber begins climbing. And then the position that the function outputs is also 0. So that means ground level, right? Because ground level is identified with the number 0 on the real line. So we should say the climber is at ground level when they begin climbing. Okay, so that's all there is to that. And then we've got one more filled in. Or one more to fill in. So let's look to the last row. So the meaning is the climber is 2 rungs below ground level 12 seconds after they begin climbing. So, well, the point in time that we're interested in is going to be t equals 12 because it says 12 seconds after they begin climbing. That's the t value. And the position is 2 rungs below ground level. Right, so remember, two rungs below ground level, that's going to be identified with the point -2 on the real line. So to fill in the mathematical statement, we can just go s of 12 is equal to -2. So really, we don't know exactly what the climber did, but based on this position function, this is one path of motion that the climber might have followed. We don't know all the information, so we can only guess. But at time equals 0, at some point the climber started at ground level and they maybe put their hand on the first rung and they got ready to climb. We know that after 6 seconds they were up on the 4th rung. So somehow in the first 6 seconds, we don't know what they did during that time, but we do know that right at the end of that first 6-second interval, they were up at 4. They were up at 4 rungs above ground level. Now maybe they just steadily climbed slowly during those 6 seconds and got up to the 4th rung. Maybe that's what happened. Or maybe they climbed up really fast, then went back down, and then went back up again. And were back up at the 4th rung 6 seconds. Maybe they took 2 seconds to climb up, 2 seconds to climb back down, and then 2 seconds to climb back up again. Like, that's possible because we aren't told what happens in between t equals 0 and t equals 6, right? We only know what happens at t equals 6. Okay, and then s of 0 equals 0. This is pretty natural to expect. Right when they begin climbing, they're at ground level, right? That's not always going to be true. Maybe the climber jumped from some other location and just grabbed the ladder, falling from the air. That's possible, but it's pretty natural to assume that in a normal circumstance, if you're modeling the position of a climber, they're going to start at ground level at time equals 0. That's pretty natural. But it's, in fact, we don't need to assume it, right? It was given to us in this example. The last thing, it says that at 12 seconds, if s of 12 is equal to -2 and the climber is 2 rungs below ground level, 12 seconds after they begin climbing, again, we don't know what happened in between the t equals 6 when they were at 4 rungs, but within the next 6 seconds of motion, they ended up being 2 rungs below ground level. That's all we know. We don't know what they did in between, but that's just all we know. Okay, so that's one example. I really want to go thoroughly through the idea of a position function because this is actually an idea that is quite often misunderstood in this course. So I'm going to go in quite detail. So we'll start another example on the next page involving a bug that's crawling along the x-axis.